So today we're going to talk about chemical reactions. And the thing that we need to understand about chemical reactions in general is that they always result in changed identities of the substances involved. So you're not just, boiling water. You're separating water into hydrogen and oxygen, which have different properties. How do we know for sure that we've created something new with new properties? One way is if there's a lot of heat or light exchanged, and that can be just a physical change like melting or boiling, but if it's a lot, it's usually going to be a chemical reaction. If a gas is released, so if you have bubbling, it's probably a chemical reaction. If you have a color change, like the way that rust changes iron from kind of a gray color to orange, or if a precipitate forms. Precipitate is when you put together two clear solutions, which we also call aqueous solutions, and you get a cloudy, solid precipitate. We actually did this in our reactions, one of our earlier labs, where we tried to figure out the reactivity of different alkaline earth metals, and they formed little cloudy precipitates in our well plates, and we'll see that more in this unit as well. So it's important to understand that for any reaction, we're not changing the number of atoms present. That would break the law of conservation of mass, and we can't do that. All we're doing is rearranging the atoms from what they were before, which is also called the reactants, to what they are after the reaction is over, which is called the products. So for example, if we look at this reaction, this is the combustion of methane, CH4, or carbon tetrahydride. So it reacts with oxygen, and all we're doing is we're sort of giving these atoms new other atoms to bond to, and probably releasing a lot of heat in the process. Okay, so how do we write equations? A couple things to keep in mind here. If we look at an example, so this is the synthesis of water. So we're making water out of hydrogen and oxygen. Again, this is a chemical reaction because we're forming new bonds. We're not just breaking intermolecular forces to make this water or forming new ones. We're actually forming new covalent bonds, so we know it's a reaction. Some things to take note of here. The physical states will be given in parentheses, so sometimes that's important, sometimes it's not. But if it says G, that means a gas. If it says L, that means a liquid. S is solid, and AQ is aqueous, which just means it's dissolved. And then the other thing to keep in mind is that the coefficients out in front give a ratio of molecules. So in this case, we have 2 hydrogen molecules reacting for every 1 oxygen molecule to make 2 water molecules. So writing a sentence equation. So you could write this chemical equation as a sentence. You could say hydrogen gas reacts with oxygen gas to produce liquid water. And you'll be asked to do that a little bit. We'll practice with that a little bit later. One thing to note here, and this kind of is like a side note, but the best place to probably talk about it, and that is, even though I'm just calling this hydrogen gas, notice it has a subscript of 2. And that's because hydrogen is only stable when it's bonded to another hydrogen atom. The same thing is true of oxygen. Okay? When it's in its pure form, it must have a subscript of 2. It doesn't have to when it's in a compound. So for example, H2O, the 2, there it does happen to be a 2 on the hydrogen, but there isn't a 2 on the oxygen. And again, it's only diatomic, or only has to be diatomic, when it's by itself in elemental form, not in a compound. So don't think that every time you see hydrogen, it has to have a 2 after it. That's only when it's by itself as pure hydrogen. The others that do this, in addition to hydrogen, we also have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So notice fluorine, the last 4 of these, fluorine, chlorine, bromine, iodine, those are all halogens. And then we just add hydrogen, nitrogen, and oxygen to that. One way to remember it is if you remember the nonsense word Brinkelhoff, B-R-I-N-C-L-H-O-F, Brinkelhoff. If you could just remember that word, that'll give you all of your diatomic elements. Okay, So let's say we wanted to convert from a sentence equation to a chemical equation. Here's our sentence equation. Fluorine gas reacts with solid sodium chloride to produce solid sodium fluoride and chlorine gas. See if you can write the equation. You don't have to balance it. You don't have to put the coefficients in, but just write the substances, and then we'll worry about balancing it later. Okay, so pause the video if you haven't and give that a try. Okay, you came up with something like this. So the fluorine is one of our Brinkelhoff, so it's going to be F2. NaCl is 1 to 1 because sodium is +1, chloride is -1. It's forming sodium fluoride, again, +1, -1, and chlorine gas, and chlorine is one of the Brinkelhoff elements, so it gets a 2 because it's by itself. So let's talk about balancing. The first rule is when we're balancing, we only change coefficients or add coefficients. We never change the subscripts when we're balancing. All right, so let's take an example here. So using this equation that we already wrote, see if you can figure out what coefficients you would have to put in front of these substances so that we have the same number of atoms on the left side of the arrow that we have on the right side of the arrow. So for example, right now we have 2 fluorines on the left, but only 1 on the right. We cannot add a subscript of 2 because that would change the ratio of sodiums to fluorides in sodium fluoride. We can't do that. But what we can do is double the amount of sodium fluoride. So go ahead and give it a try. See if you can figure out, I've already given you a big hint how to start, but pause and give it a shot, see if you can balance. Okay, so pretty much already gave you this clue. There should be a 2 in front of sodium fluoride, and that balances the fluorines, right? 2, and then the coefficient gets distributed to the whole formula. So this 2 out front means we have 2 sodiums and 2 fluorides, or you could say we have 2 sodium fluorides. But for balancing purposes, probably best to say we have 2 fluorines, because that's what I was trying to balance in the first place. Now we also have now 2 sodiums, again, because you distribute just like in algebra. If I only have 1 sodium on the other side, hopefully you realize, oh, I've got to balance that with a 2 in front as well. Can't put a subscript, have to make it a coefficient. Which also gives me 2 chlorides, because again, we distribute the coefficient into the whole formula. But that's a lucky thing actually, because we also have 2 chlorines on the right side. Okay, so that one is balanced. And always want to double check when you're done to make sure that you can't reduce it. In other words, this is a 1 to 2 to 2 to 1 ratio. And so if it were like 2 to 4 to 4 to 2, then we could reduce it by dividing everything by 2. But since we have 1 coefficients in here, we can't reduce it. So we're good. Okay, let's try another one. Go ahead and pause and see if you can figure this one out on your own. Okay, the order I went in was, and the one you picked to go first doesn't really matter too much. We'll talk about some exceptions to that, but I picked oxygen to balance first. And so I have 3 on the left. So in order for me to have 3 on the right, I had to put a 3 in front of barium oxide, right? Well, that also gives me 3 bariums, so I put a 3 over there on the left. And then the last step is check my aluminums. I have 2 on the left and only 1 on the right, so I'm going to go ahead and put a coefficient of 2 in front of aluminum. And again, check to make sure it can't be reduced, but because we have a coefficient of 1, you can't reduce that at all. Okay. All right, let's try this one. And before you pause and try this one, I want to give you a pretty big clue here. If you have a polyatomic ion, like from our list that we memorized, such as phosphate, and it shows up on both sides of the equation, just treat that as one thing. Don't try to balance the phosphorus and the oxygen separately. Keep it intact as phosphate and just balance the number of phosphates on both sides. It'll save you some time. So go ahead and pause here and give it a shot. Okay, so let's see. I decided to balance my phosphates first. So because I have 2 phosphates on the right, I went ahead and put a 2 in front of sodium phosphate to give me 2 phosphates on the left. And then that gives me 6 sodiums, because again, I distribute that 2. And so I have to put a 6 out in front of NaCl. That gives me 6 chlorides, which means if I have 2 in calcium chloride, I would have to multiply calcium chloride by 3, because 3 times 2, we multiply coefficient by subscript. That gives me 6 and matches up my chlorides. Then finally, my calcium is already balanced because that 3 matches the 3 subscript on the other side. Okay, I'm going to go ahead and put, oops, gave that one away. Go ahead and give you a chance to do that one. Go ahead and pause. Okay, so for this one, I'm going to go ahead and say, let's put a 2 out there to balance my sulfur. So this one's a little bit weird because I only have sulfur in one place on the left, but I have it in 2 places on the right. So I have 2 sulfurs on the right, only 1 on the left. So sulfate actually, I'm sorry, the sulfur now has 2 because I have 2 on the left. That is then going to bring my number of hydrogens up to 4, so 2 times 2. And so I'm going to have to multiply my water by 2 to have 4 hydrogens on the right. And then, let's see, then my copper is balanced. My sulfurs are balanced. My oxygens, I have 2 times 4, okay, is 8 there. And then I have 4 here in this sulfate, and another 2 plus 2 is 8 total on the right side. So I said, if you have a polyatomic ion on both sides, then just kind of treat it as one particle. The problem became with this one, though, yes, we had sulfate on both sides, but we also had sulfur in another place. So I kind of had to balance the sulfur and the oxygen separately this time. Okay, go ahead and give this one a shot, and this will be our last practice. And actually, let me give you one hint here. Oxygen, this is a combustion reaction. It contains carbon, hydrogen, and oxygen. And whenever you have a combustion reaction like this, balance oxygen last. And the reason for that is whatever coefficient we end up putting in front of oxygen only affects oxygen. And so we can balance it last, and it makes it just a little bit easier for us. Okay, so go ahead and pause and try that one. Okay, so it doesn't matter whether we start with carbon or hydrogen. I'm going to start with carbon. So I put a 3 out in front of carbon dioxide, and that gives me 3 carbons to match the 3 on the other side. And then I balance hydrogen by putting a 4 in front of water. That gives me 8 hydrogens on both sides. Now be careful here. On the right, for my oxygens, I have 3 times 2 is 6, but I also have 4 more over here. So we have to add those 2 together. So 6 plus 4 is 10. So what times 2 would give me 10 on the left side? And of course, that answer is 5.